Okay, I think it will be time to start, Andre. So it's a pleasure to see you on this Zoom seminar, which are common with the FreeFM Days and the lab. And you are very welcome to present your work on this complex mechanical structure.
Thank you very much indeed, Francois. Frederick, it really is a huge pleasure to be able to contribute to this seminar. Such a great pity that we can't be all together in Paris, really unfortunate. So let me thank you, Frederick, Francois, for inviting me along. So I should share my screen at this point, I presume. So I'm getting a message, host participant disabled screen sharing, so somebody should.
Of course. No, I'm stupid. Sorry. I have to say participant here. 2 seconds. Okay. You can do. Now you are co-animator.
Okay.
Except if I make a mistake.
Right. Okay. Looks good.
Yeah. We look your screen.
Okay. Okay. So let me now. I'll go to presentation mode.
Okay.
Is this okay now? Is it visible?
It's okay now.
And you can hear me.
Yeah.
Okay. So this talk concerns what are known as implicitly constituted fluid flow models, and I'll be talking about the analysis of these models and finite element approximation. So this is based on joint work with several people. So Mira Bulicek and Josef Malek at the Charles University in Prague got me going in this area. And I think this really is a very exciting and interesting area with lots of open problems. In the area of analysis of partial differential equations that arise in these models, there has been a certain amount of work, but in the area of numerical analysis of finite element approximations, in particular of these models, there has been really very limited amount of work. So somehow the purpose of this talk is to draw this to your attention as perhaps an interesting area. So I was in the area of numerical analysis collaborating with Lars Diening at Bielefeld and Christian Kreutzer at Dortmund. Tabea Chirpel was my doctoral student at Oxford, and she's now at Bielefeld with Lars Diening. Alexei Gaska-Orozco was my doctoral student here at Oxford, and he too moved to Germany, to Erlangen-Nuremberg. Patrick Farrell is my colleague here at Oxford. So perhaps a good place to start in the description of these implicitly constituted fluid flow models is to highlight the fundamental equations that underlie these models of fluid flow: balance of linear momentum, conservation of angular momentum, conservation of mass, and the principle of maximal entropy production, which are the equations that you see on this slide. So the first equation, which in the case of Newtonian fluids gives rise to the Navier-Stokes equations, is this equality here: balance of linear momentum, the symmetry of this tensor T, and T here is the stress tensor, the Cauchy stress tensor, is conservation of angular momentum. Rho is the density of the fluid, U is the velocity, and F is the density of external forces, so maybe gravity. The second equality is conservation of mass, and this final equality here is this principle of maximal entropy production. Psi here is the entropy production, and so in agreement with thermodynamics, this entropy production is supposed to be greater than equal than 0, which means that entropy in this closed system will always be increasing. So here, for the purpose of this talk, but I'll talk about extensions later on, we shall assume that we are in the isothermal case, so the temperature will be assumed to be constant. In a second, I shall also assume, again for the simplicity in this talk, that the density is constant, so there will be some simplification in these equations. In particular, if the density is assumed to be constant, rho being here the density, rho sub t vanishes, and if rho is a constant, then this second equation becomes just divergence u equal to 0. And then also, if you are assuming, again, for the simplicity in this talk, that you are in the steady state case, that the time derivative also vanishes here. So this first term will also vanish. But we'll see that simplification on the next slide. So let me just comment once again on the notation. So once again, rho here is the density, u is the velocity, t up here is the Cauchy stress, f is the density of external forces, d of u appearing here is the symmetric velocity gradient, also called the rate of strain tensor. Psi, this function psi here, is called the Helmholtz free energy, and psi, as I said, is the entropy production. So if you assume that the density is constant, then not only this equation, the second equation simplifies, but if rho is constant, then psi of rho is constant, and the time derivative of that becomes 0. So this principle of maximal entropy production also simplifies because you lose this second term here on the left-hand side. And this, again, for the purpose of this talk, will be the set of equations I shall be looking at. So we are looking here at a special case when the problem is not only in the isothermal regime, but we are dealing with a homogeneous fluid, the density is constant, and let's suppose that we are at steady state, and then from those more complicated equations, we collapse to these three equations here, where T, once again, is the Cauchy stress tensor, which is assumed to be symmetric, and psi is the entropy production, which is greater than or equal than 0. But then in order to close the system of equations, you also need a constitutive relation. And the constitutive relation is some kind of relationship that relates the Cauchy stress tensor with d of u, this symmetric velocity gradient. And depending now on what kind of fluid you are describing, this constitutive equation will vary from fluid to fluid. Before I give you examples, let me just make one remark. What is usually done is the Cauchy stress tensor is decomposed into one part here, S. So think about T as a matrix. You decompose this matrix T into a part that has 0 trace. So the trace of S, in the sense of matrices, trace of S is equal to 0. And then the trace of the original matrix T is put into this part here. So it's sort of a decomposition of the Cauchy stress into this traceless part, which is called the deviatoric or shear stress. And then this other part is the pressure. And so what we will have in a moment is various constitutive relations that relate S here to d of u, depending on the fluid. The simplest possible case is to take a Navier-Stokes fluid where you have a linear relationship between this deviatoric or shear stress and d of u, the symmetric velocity gradient. So S in that case is 2 mu, when mu is the viscosity coefficient, times d of u. And so if you take this S here and you plug it back into this decomposition of the Cauchy stress, so T, now with this formula for S and minus Pi is plugged back into the equation, you arrive at the Navier-Stokes equation. So the first term is copied from above, and div T gives rise through this decomposition to 2 terms minus mu times Laplace of the velocity plus gradient of the pressure is equal to F. Divergence U is equal to 0. And now the question is, what happens to this third relation? Have we satisfied this relationship? Is this model consistent with the laws of thermodynamics? So let's just check what happens with T scalar product with d of u. Okay, so psi, the entropy production by definition is T scalar product with d of u in the sense of matrices, meaning that you multiply appropriate elements of the matrices together and you add them up. So this is the definition of this double dot notation. So scalar product of T and d of u. T, because of this decomposition, is S minus Pi, but then if you take the inner product of Pi contained in T with d of u, the scalar product of I and d of u is the trace of this symmetric matrix d of u, but the trace of d of u is really just the divergence of u, and the divergence of u is equal to 0 by assumption. So basically, when you take the scalar product, you lose this pressure part, and what you end up with, T scalar with du becomes S scalar product with du. And then you could plug in this constitutive relationship here into this formula, and you can do this in two ways. You could either plug in S instead of this S, or you could express D of U in terms of S, and then you could plug in D of U and eliminate D of U in terms of S. So what is written here is basically a compromise between these two options. You take one half of one option and the other half of the other option, and what you end up with is not 2 mu times d of u squared, but just 1 mu times d of u squared, and then the other mu d of u squared is written as 1 over 4 mu times the norm of this matrix. So these the single bars denote what is called the Frobenius norm, or like sum of squares of entries in the matrix. So clearly this is a non-negative expression, which is good news because we have satisfied the third law here also. But just for the purpose of the calculations that will follow, let me note just a trivial observation that this expression here can be bounded further below by taking the minimum of mu and 1 over 4 mu, so you have a single constant that multiplies d of u, the norm of d of u squared, plus the matrix norm of s squared, and clearly this is non-negative. So in the case of this Navier-Stokes fluid, these exponents here are 2 and 2. And that is associated with the fact that we have this linear relationship between the deviatoric or shear stress and the symmetric velocity gradient. So this is what happens in the case of Newtonian fluids. There are, however, lots of other fluids. So basically you go around the house, you open the fridge, and you will find various creams, and you go to the bathroom, you will also find creams, or you go out to the shed, you will find paints and various exotic fluids, which depend in ways which are not similar to how water behaves. So here's one, this is called the Paolo or Oswald-de-Wahle fluid, where you have a Paolo type relationship. In the special case, if you took R to be equal to 2, this nonlinear term would vanish and you would go back to a Navier-Stokes fluid. So this is sort of a generalization. There are generalized Paolo fluids where instead of this exponential behavior here, you have some perhaps continuous function, which is typically monotonic increasing of the norm of d of u squared. These are called generalized Paolo fluids. There are situations where d of u is given as a function of s rather than s being given as a function of d of u. There are, there's a whole zoo of these models. There are also models where this is not just a continuous relationship, but there's a set of inequalities which in fact describe a discontinuous relationship between S and D of U. So here's one. This is called the Bingham model, or Herschel-Bulkley fluid, where the situation is the following. As long as the magnitude of the shear stress is below a certain critical threshold called the yield stress, D, that is D of U, the symmetric velocity gradient is equal to 0. Once the magnitude of S exceeds this threshold, then the fluid starts to move according to a certain formula. So what I have next to me, I don't know whether you can see me, not just the slides here. So I don't know whether you can, do you see this? So it's toothpaste. So what I'm doing, I'm pressing this toothpaste and there is no lid on it. I'm pressing this toothpaste and there's nothing coming out of the tube. I keep on pressing and I'm pressing and pressing and nothing happens until I press hard enough. And once I have pressed hard enough, the fluid starts to move. So you can see the fluid coming out, it flows. And so this is an example of a Bingham fluid. So what is interesting about this Bingham fluid example is that you can, so this is just a little algebraic exercise. It is possible to describe this pair of inequalities written here as a single implicit relationship between D and S given by this formula, and this plus here is a positive part of this expression. So I shan't dwell on the details. You can verify that this single equality encapsulates these two inequalities here. So the reason I've written this down is to highlight the fact that in addition to Navier-Stokes, you have these nonlinear relationships, and sometimes these nonlinear relationships can be very nonlinear. In fact, they can be implicit. what is interesting about them in all of these examples, that even though you may have a nonlinear relationship, this nonlinear relationship, at least in these situations, is always a monotone relationship in the following sense. So in the case of the Navier-Stokes equations, we have a linear relationship. In the case of these parallel fluids, we have a nonlinear relationship, which is a sort of a monotone graph here. In the case of these Bingham fluids, you see this jump in the graph. So the shear rate remains at 0. You keep on raising the stress up until this point where the yield stress is attained, and then the fluid starts to move according to one formula or according to a different formula. So in all of these cases, we have monotone functional relationships. Some of them are discontinuous, and the idea would be that instead of thinking of functional relationships, which may be continuous or discontinuous, think about all of these graphs as continuous graphs. So I'll come to this in a moment. But let me first of all reference these important works by Rajagopal and Srinivasa, where these ideas were first put forward in the context of mechanics of fluids. There's also PD analysis of these models by Mira Bulicek and Josef Malek in Prague, and Piotr Gwiazda and Agnieszka Świerczewska-Gwiazda in Warsaw. There are two papers here. One is on steady models and the other one is on time-dependent models. So let me try to be a bit more precise about the problem that I'm interested in. So let's suppose that we have a bounded open Lipschitz domain, the flow domain, that we are either in 2D or in 3 space dimensions. Here's our equation again with this decomposition of the Cauchy stress that I mentioned to you. And what we shall suppose is that there is a relationship between S, this shear stress, and the symmetric velocity gradient, d of u, which is in some kind of nonlinear form, g of S d of u is equal to 0. So it's an implicit constitutive relation. So once again, the notation, u is the velocity field, p is the pressure, S is because of this conservation of angular momentum, S is symmetric. This is our shear stress, and d of u is the symmetric velocity gradient. So what we will do is, instead of thinking of an implicit constitutive relation, we shall associate with this implicit constitutive relation a monotone graph. And these were these pictures that I tried to indicate on this previous drawing. So we shall identify the implicit relation with a graph, which is defined on the Cartesian product of d by d symmetric traceless matrices, which is where S comes from, with d by d symmetric traceless matrices where d comes from. So this is our implicit relationship, and we shall identify that with a graph where, if you like, on the horizontal axis you have d, and on the vertical axis you are plotting S, and you have some kind of monotone relation. So what we'll assume is that this graph A is a maximal monotone graph, R graph, and this R graph property concerns the growth properties of the graph, but I'll be precise about that in a second. So there are certain axioms that are assumed here. So it is assumed that the point 0, 0 is contained in the graph. And this was the case in all of these pictures that you saw on the previous slide. We shall assume that the graph is a monotone graph. So this is the monotonicity property of the graph. The third property is maximal monotonicity, which simply conveys the fact that there are no holes, there are no gaps in the graph. So if you like, you could put your pen on the paper and you could, without lifting the pen from the paper, you could draw out a continuous graph, even if it's discontinuous as a function. And the fourth property, and this is where this letter R comes from, is associated with this principle of maximal entropy production that I illustrated in the case of Navier-Stokes equations, when we tested this, when we checked the scalar product and we were looking for a lower bound on S scalar D, and we found such a lower bound with exponents 2 and 2. Well, what is assumed here is that there is a similar sort of property in the graph, that the scalar product is somehow bounded below by the matrix norm raised to the power R and the matrix norm of S raised to the Hölder conjugate R prime of R. So these are the assumptions on the graph. So let me now come to the numerical approximation to the problem. So the first issue is that because there are potential discontinuities in this graph, even though it may be monotone, it may be a sort of a discontinuous function. Sorry, there's some noise coming from the background. So we shall approximate this implicit constitutive law with a sequence of explicit laws Sn. So the first step is somehow to mollify this potentially discontinuous graph. So one way of doing this is, for example, you make a measurable selection from the graph and you take a convolution with some maybe compactly supported function in L1. And so pictorially, you are replacing this discontinuous constitutive law with something that is now continuous. And then eventually we shall pass the limit with this modification so that this red curve in the limit steepens up to the discontinuous graph. There are lots of ways of doing this. Here's another way of modification. This is called the Yoshida regularization of the graph, where you are replacing this discontinuous graph with something that is now continuous. And once again, you can pass the limit with n and approximate the discontinuous graph. So in some way, you first of all mollify the discontinuous graph. The second step in the construction is to approximate the problem on a grid. So you have your flow domain and you take your mesh generator and it generates a computational mesh consisting of maybe triangles in 2D or simplices in 3D. And you would like to discretize your partial differential equation on this finite element grid. So there is a discrete velocity space V sub h, where h is the granularity of the grid, and this velocity space consists of piecewise polynomial functions on this grid, and VH is contained in the natural function space for the velocity. It's this Sobolev space with perhaps a zero boundary condition on the whole of the boundary. And then you have your pressure space Q sub h, which is contained in the natural function space for the pressure. It is a Lebesgue space with a certain index. I'll come to this index R tilde in a second. The zero down here simply denotes, because the pressure is only determined up to constant, somehow you have to fix the value of the pressure, and you can fix it in various ways. Perhaps you demand that the integral mean of the pressure is equal to zero, or in some other way. So the zero is not zero boundary condition as in the case of the Sobolev space, but it concerns the fact that you are fixing the pressure because an arbitrary constant in the pressure. So there are certain sort of assumptions on these finite element spaces. It is assumed that the union of these velocity spaces as you run through all mesh sizes is dense in this Sobolev space, and the sequence of the union of these pressure spaces as you run through all grid sizes is dense in the appropriate pressure space. So let me just say a few words about this R tilde, because this unfortunate R tilde will somehow haunt us throughout the talk. You don't see this in the case of the Navier-Stokes equations, where R would be 2 and R tilde would also be 2. But because we are now no longer in this nice Navier-Stokes setting, we have R, the index of the Sobolev space, we have R prime, the Hölder conjugate of R, and this R tilde is by definition either R prime if this index R is greater than equal than the dimension, or if you are below the dimension, then it is not R prime, but perhaps a smaller number, which is this dr over twice d minus R. Okay. So the first step in the analysis, because what I'm interested in is the analysis of the convergence of finite element approximations, is to understand what happens at the level of the partial differential equation itself. So how exactly would you derive an energy inequality if you encountered such a model? So you would take your balance of linear momentum equation. So for Navier-Stokes, this would be the Navier-Stokes equation, and you would test it with the velocity field itself. Now, I have to emphasize that this is a formal calculation because at this point it is not clear that u itself is a valid test function, and we will have problems with precisely this issue. There will be instances when the velocity is not a valid test function, but this at this level is a formal calculation. So we test the equation with the velocity field, and you can see here f dotted with u integrated over the domain. In the pressure term, we have performed partial integration and moved the gradient from the pressure across onto this test function u. There's a sign change. There are no boundary contributions because u is supposed to be 0 on the boundary. In the viscous term, we have performed integration by parts. There was minus divergence of s. Now there's a sign change and the divergence moves over onto u. It becomes a gradient, but then because s is symmetric, you can replace the gradient by the symmetric gradient. And this is the convective term, which is tested with u. Now I have highlighted two terms in blue. And you can see from this that because divergence u is equal to 0 pointwise, this blue term will trivially vanish. This first blue term also vanishes, it turns out, and this is just a simple calculation again because of the fact that the divergence of u is equal to 0. And therefore, you lose the first blue term because divergence u is 0, and you lose the second blue term because divergence u is equal to 0, and you are left with this equality. At this point, you can appeal to this fourth axiom of this monotone R graph and bound S scalar du below by this quantity here, the Lebesgue LR norm of du raised to the power r, and similarly for the stress tensor in the conjugate index. And then, so the objective would be to hide this u into the left-hand side. So it's basically Hölder's inequality, if you like, or you can just recall the definition of a negative Sobolev norm of f and bound this expression above like so. And then using Young's inequality, you can kick this d of u back from the right-hand side into the left-hand side, and you end up with a very nice energy inequality where the data f bounds d of u and s. So then the question is, how exactly can you replicate this argument on the discrete level? Please bear in mind that when we work with finite element approximations, this d u will not be pointwise equal to 0. So the fact that these two blue terms vanished was relying on the fact that d u is equal to 0. So let me just for a second reinstate the two blue terms. So this is one blue term. As it turns out, in the theory of mixed finite element methods, this is a familiar issue, and this term can be easily made to vanish simply by demanding that if you replace u by uh and p by ph, dvuh, which comes from a finite dimensional space, is orthogonal to ph. And we'll see this on the next slide. The vanishing of this first blue term relies on dvu being equal to 0, and if dvu is now dvuh, and dvuh is now not pointwise 0, it is not clear how this term will vanish. And we'll come to that in a second. So the purpose would be to replicate this argument now at the discrete level. So as I said, concerning the second blue term, this is sort of familiar territory in the field of mixed finite element methods. One can simply make sure that the velocity space and the pressure space for the finite element method are chosen in such a way that this equality is true. So basically the divergence of the discrete velocity is perpendicular, orthogonal to the pressure space. And there are lots and lots of ways of doing this. So this now goes into the theory of mixed finite element methods. There is lots of choice in terms of various finite element spaces that you could use in order to ensure that this is true. If you are more ambitious and you would like dvuh to vanish pointwise, now this is sort of slightly more demanding, but there are constructions of finite element spaces that ensure that dvuh is pointwise divergence free. So for example, these constructions by Scott and Vogelius, or more recently by Guzman and Neelan, where they are, instead of piecewise polynomials, using piecewise rational functions which are sort of piecewise on the grid to ensure that div is pointwise divergence free 0. In the case of this sort of option B, even though we have dealt with the second blue term, we still have an issue with the first blue term. How exactly to knock out this first blue term when div UH is not pointwise equal to 0? Now, there are tricks. Again, these come from the theory of Navier-Stokes equations. For example, if you look up Teman's book on the Navier-Stokes equations, this is described there. What is done is, instead of using div U tensor V dotted with W, you take 1/2 of that expression, and then in the other half, you perform partial integration. So what you have is basically a compromise. You take 1/2 of the original convective term and another half of it, which comes from integrating by parts. And when div U is identically 0, this modified, or sort of this partial integration-based trilinear form is exactly the same as the original one. And it also has the nice property that when the 3 entries in this trilinear form are the same, then this expression is obviously equal to 0. And this is precisely the property that we need, because what we need is, even if div UH is not pointwise divergence free, we need such an expression to vanish. So if we are in option A, what we will do is replace the original trilinear form by this modified trilinear form. So I'm going to state the convergence theorem in a second, but let me just be precise about the numerical method. So what we are doing is N is coming from this graph approximation from steepening up the modification in the graph, and H is the mesh size. So we have sort of a 2-parameter family of discretizations for the velocity with the index N that comes from the graph approximation and H from the grid, and similarly for the pressure coming from the appropriate finite element spaces that live in the appropriate Sobolev spaces that satisfy this equality here. So you see the graph approximation Sn of S, you see this modified trilinear form for the convective term, you see the approximation of the pressure term and the source term on the right-hand side, and you see the discrete imposition of divergence U equal to 0. So here's the theorem, and what we have is the following. So if we are, let me look at case B first of all. If we are using finite element functions for the velocity, which are pointwise divergence free, then as long as R, this is the Sobolev index here, is greater than this critical value of 2d over d plus 2, then we have certain weak convergence results, which I shall come to in a second. And in case A, when we are only discretely divergence free, then for R greater than a slightly larger number, 2d over d plus 1, we have these weak convergence results. And the reason for this discrepancy between these two cases comes from the fact that in case A, we have replaced the original trilinear form by this modified trilinear form, and the boundedness properties of this original trilinear form are slightly worse than those of the original trilinear form in the convective term that you encounter in case B. So one way or the other, you have weak convergence of the velocities in W1R, you have weak convergence of these approximate stresses to a stress that lives in a function space, you have weak convergence of the pressures, and this triple USP satisfies the weak formulation of the equation. Furthermore, this pair D of U, so the symmetric gradient of the velocity, and this S that you have converged, this pair lies on the graph. So let me draw your attention to the fact that the test function in this weak formulation of the problem do not come from the same space as for the velocity itself. So U comes from W1R, 0, whereas the test function comes from W1. You remember this R tilde, which is sort of like the Hölder conjugate, but not quite. So this is the conjugate of that modified Hölder conjugate. So the conjugate of the conjugate is the original number, and because R tilde is not the same as R prime, the prime of that is not the same as R. So this R tilde prime is unfortunately not R. So the test function and U unfortunately need not come from the same space, and this will cause problems. So in the remaining time, let me just run through the proof of convergence, because I think it's quite interesting. So the first step in the analysis is to fix the mesh size and pass to the limit with the graph approximation. So as long as the mesh is fixed, we are operating in finite dimensional spaces. the existence of u and h contained in the velocity space, so the existence of a numerical solution, follows by an application of a modification of Brouwer's fixed point theorem. This is sort of a nice result in the book of Giraud and Raviard. So it's a nice little consequence of Brouwer's fixed point theorem. And you can show, basically using the same argument as the one that I showed you, that you have such a bound on the sequence of velocities and stresses, using this axiom 4 from the property of the R graph. And then, because we are operating in finite dimensional spaces, it follows from the Bolzano-Weierstrass theorem. This is sort of a sequence in a finite dimensional space, that you have strong convergence or pointwise convergence, weak convergence is all the same in this norm LR. For the second term, you have to appeal to Alaoglu's theorem, because even though d of UH comes from a finite dimensional space, this S is some function. So these guys converge now weakly to an object, and it is possible to identify this object as precisely S of DUH using Minty's method. So this is the first step in the analysis. So now we would like to pass to the limit with H. So, but before doing so, let me just remark that one can also pass the limit with N, as we are doing here in this inequality, using weak law semi-continuity. So this is what is done here. And by doing so, we arrive, by passing to the limit in N, we arrive at this next inequality that we have. So it follows directly from step 1 by weak law semi-continuity that we have this inequality. So now we have boundedness of this sequence, and we have boundedness of this other sequence. Again, by appealing to Alaoglu's theorem, these d of u's will weakly converge to d u, and these s of duh's will weakly converge to something. Let me denote that something by s bar. What is not clear at this point is whether this pair d of u and s bar lies on the graph. Now, this is very important, because if this is not the case, then the constitutive relationship has been violated. So the question is whether this pair d of u and s bar that you have converged to weakly lies on the graph. So in other words, is it true that this s bar is s of d of u? Now, in order to show this, we have to do some sort of technical steps. So in order to show that d of u s bar lies on the graph, what we will do is, motivated by the fact that we are dealing with a monotone graph, consider this object here, s of duh minus s of du, scalar with d uh minus u. By using Hölder's inequality and the bounds that we have from step 2, what we have is, so it's a simple application of Hölder's inequality, we can bound this scalar product by a constant, because each of these entities is bounded above in this one in LR and this one in LR prime, Hölder conjugate. So this whole expression is bounded above by a constant. We also know that this AH is greater than or equal than 0. So I could have dropped these absolute value signs, because this guy here is non-negative, but I wanted to emphasize the fact that what we are dealing here is a bound on the L1 norm of a certain quantity. And if a sequence is bounded in L1, unfortunately, it doesn't automatically follow that you can extract perhaps a weakly convergent subsequence. What comes to the rescue is a wonderful result called Chacon's biting lemma, and I would like to refer you to this beautiful paper by John Ball and Francois Murat on the Chacon biting lemma, which says the following, that even though you may not be able to extract weakly convergent sequences in L1, what could nevertheless be done is you can consider an increasing sequence of subsets of the set omega, which eventually exhausts the set omega, in the sense that the measure of the discrepancy between omega and the kth member of the sequence converges to 0. But then on each of these omega k's, you can find a subsequence for which this object up here now weakly converges not on L1 omega, but on L1 omega k. So this is sort of good news, but we still have a problem. And the problem is the following. So what we would like to do now is go back to the equations and use monotonicity and the equations together. The problem is that if you were to use the equations, you would need to use u as a test function, but u is not necessarily a legitimate test function. So you can't just plug in u as a test function into the equation. So what we need to do, so sort of a further technical hurdle, we have to go through a process called Lipschitz truncation. And so why is this Lipschitz truncation needed? I think I've sort of explained this. So if R is small, then this difference UH minus U is not necessarily contained in this Sobolev space where the test function should come from if you were to use U as a test function. So this is not a valid, this is UH minus U is not a valid test function. So you can't just plug it in as a test function. So the idea would be to approximate this UH minus U with a Lipschitz function so that it becomes a valid test function. But you need to do this in such a way that when you approximate it, you only alter UH minus U on a set of small measure. So for example, you can't just modify this UH minus U with some smooth function, because that will change this UH minus U on perhaps a large set of uncontrollable size. So what comes to the rescue is a result by Acerbi and Fusco, published in this collection of papers up in Edinburgh, which is about this Lipschitz truncation method. And what we ended up using in the analysis of this convergence proof is we had to build a discrete counterpart of this Lipschitz truncation method of Acerbi and Fusco. So what happens in this Lipschitz truncation method of Acerbi and Fusco is the following. So you have a Sobolev function, maybe from W11 with a zero boundary condition, and you consider the maximal operator, it's Hardy Littlewood maximal function associated with the gradient, which is defined like so. So this has a nice property in that it is then V. So V is then Lipschitz continuous function on this set. So these sets are the sub-level sets corresponding to lambda. So consider lambda and you consider values of m, the maximal function below that value lambda, and V is Lipschitz continuous on these sets. The proof of this comes from this inequality. V of x minus V of y in absolute value is bounded above by the maximal function of the gradient of V at x plus the maximum function of gradient V at y times x minus y. So as long as you are on this set where the maximal function is bounded by lambda, you have Lipschitz continuity. So let me denote by G for good. So this is the good set. So on the good set, you have Lipschitz continuity, and then the idea of Acerbi and Fusco is to use Kirschbaum's extension theorem to extend from this good set the function on the whole of the domain as a Lipschitz function. So this is the idea. So then the good news is that as long as you are on the good set, V lambda and V coincide. And then the other piece of good news is that when they don't coincide, the measure of the set when they don't coincide is small. So V lambda is this Lipschitz truncation of V. The bad news is that the Lipschitz truncation of a finite element function, unfortunately, does not belong to the same finite element space that the original function belonged to. So you have to go through some acrobatics to ensure that you end up in the same finite element space. So I'm going to come to this definition of this discrete Lipschitz truncation in a second. What we are using here is a special projection. It's a discretely divergence preserving projection, which comes from the theory of mixed finite element methods. So this is this operator P sub h that takes a function and puts it into a finite element space in such a way that somehow the divergence is preserved. So what we'll do is consider this difference UH minus U that we saw on the previous slide, project it using this projector, and denote this by E sub h. So here's this Lipschitz truncation result that comes from this paper with Lars Diening and Christian Kreutzer. And what it says is that you can take your EH from the previous slide, you perform this Acerbi-Fusco Lipschitz truncation of that function, you project it back using this projector that I described to you on the previous page, and you end up with a finite element function which has some nice properties. It is Lipschitz, but with a controllable Lipschitz constant, which is between these two values. And most importantly for us, the measure of the set where this finite element function does not agree with the original function is quantifiably small. So this is this red property. So I'm coming now to the end. So let's go back to this quantity A sub h that we saw previously. So what we'll do is consider EH, this pi h of UH minus U, which is from the finite element space. We perform a discrete Lipschitz truncation of this function at some high level. 2 to the power j is the level at which you are discretely Lipschitz truncating this function. And what you can show is using various bounds on this quantity A sub h that you have this sequence of inequalities. So we take A sub h here, which is non-negative, to the power 1/2. We split it into 2 bits, one on the good set where the discrete Lipschitz truncation agrees with the original function, and on another set where they disagree. We perform Cauchy-Schwarz. That's so this is this inequality coming from the first integral. We perform Cauchy-Schwarz also to get this term here. Then we use properties of the Lipschitz truncation to show that this quantity here is bounded in a nice way by 2 to the power minus j over r, and then use the property from this discrete Lipschitz truncation to argue that when these guys do not coincide, this discrepancy, the measure of the set where they don't coincide, is small. So what we find, therefore, is such a bound on this AH, and this is valid for all values of j coming from this Lipschitz truncation. So you can pass to the limit with j, and what you find is that this AH, this quantity here, must converge to 0 almost everywhere. So this is good news, because now you have almost everywhere convergence of this quantity. Also from the biting lemma, you have weak convergence on subsets. And therefore, what you find is, using Vitali's theorem, putting together weak convergence with almost everywhere convergence, you get strong convergence of this quantity to 0. And then recalling the fact that you have weak convergence of S of DUH to S bar and D of UH to DU, you deduce this equality here. Then you can appeal to the property that you have a maximal monotone graph to deduce from this last equality that, in fact, this limiting object D of U that we were worried about earlier on does in fact lie on the graph almost everywhere on these bitten sets with bits of omega bitten out, these omega k sets. And then using a Cantor type diagonal argument, what you can show is that in fact you have inclusion of these guys not only on omega k but almost everywhere on the graph. So this is basically the end of the proof. Now, I realize that I'm almost out of time, so let me just comment on some extensions of these results. So we have extended these results with Tabea-Chapel to time-dependent problems. And then in the second paper, we have looked also at the unsteady case with other mixed finite element approximations, where we were using, instead of a velocity pressure approximation, a 3-field approximation involving a finite element space for the stress as well. And then in this third paper, we also looked at the non-isothermal case. So there was a temperature equation, and again, convergence was proved. So there are some numerical experiments which are on the next slides, but I think I'm out of time. So let me stop at this point, and thank you very much for your attention. If you ask me questions, maybe I can show you some computation. So thank you ever so much for your attention.
So thank you, Andre. Now it's time for question. And I think, of course, I'm really interesting to see the numerical result, but I think there are more questions on the theoretical part. So no question?
Moi, j'en ai une, Olivier.
Moi, j'en ai une.
Yes. Okay. Complex fluid is not really my specialty, but if you want to have fluids with memory, I suppose you need time variable, the time variable. I suppose you can extend what you did to time-dependent problem, can't you?
Yes, yes. So indeed, this first paper here on the list, so the first blue reference concerns time-dependent problems, but these are still not problems with memory. So I think if you were to introduce memory, it would be more like an integral differential equation with some kind of memory kernel. Is that what you're thinking of, perhaps?
Yeah, maybe, yeah.
So one could do that. We haven't done that. What can I say? I think there are just so many of these models. You can go in so many different directions. And what you are asking is obviously a very relevant class of models.
Thank you, Andre.
Thank you.
So Albert, you see, you have to.
So very beautiful talk. So I understand you have absolutely no convergence rate. Do you that's maybe going to the numerics. Do you observe them? Do you observe optimal rates of convergence?
Okay, I'm glad you asked this, Albert. So what happens is, obviously at this general level, you have convergence to a weak solution. There is no uniqueness because these assumptions that have been made are not sufficient to guarantee uniqueness of weak solutions.
Okay.
So we have done numerical experiments and we see convergence, and we have tested. In fact, you could look at the paper. We have tested rates of convergence, and what we see is that you do get the expected rate of convergence, optimal rates of convergence when you have maybe sort of a synthetic model problem with a pre-designed solution. You do converge to the solution with the expected rate of convergence. But when there is a unique solution, you will converge to it. We haven't done a convergence analysis because in this setting, there is no unique solution. So it's difficult to talk about which solution exactly will you be converging to. But in the numerical experiments, we do see optimal rates of convergence to the solution.
So, Andre, yeah, can you see some numerical result, and which numerical scheme did you use to solve this problem? Because this is not so simple. I tried maybe 2 or 3 years ago, and I don't succeed in less than 2 days. So I think it's a difficult problem.
Exactly. I think we can share your experience, Frederick, in some of these problems, especially for small values of R. For example, these Bingham fluid type problems are extremely horrible to solve. So we solved it using this Firedrake software. We are using sort of Scott-Vogelius elements typically on barycentrically refined meshes. The meshes were generated with something called a GMSH mesh generator. We used the Newton solver. I think the residual was if it falls below something like 10 to the minus 8, we stop the Newton iterations. And for the linear solvers, we were using UMFPAC.
Yeah.
So for the stress, we were using P1 elements, for the velocity P2 on these barycentrically refined meshes, and for the pressure, we were using P1 elements discontinuous.
Okay. So this is a solution.
So this
problem.
is a solution for an unsteady problem. Navier-Stokes on the right-hand side. Navier-Stokes on the left-hand side. So Navier-Stokes on the left-hand side, and what you see here is an implicitly constituted model, which is sometimes Navier-Stokes, sometimes Euler, sometimes Bingham, depending on which region of the domain you are in. So near the boundary, it's a Navier-Stokes fluid. In the middle of the domain, it's an Euler or a Bingham fluid, depending on whether you are below or above this critical parameters. It's a sort of a combination of everything.
Yeah.
So there's a discontinuity in the graph, and we had to use something called Papa Anastasio regularization, which is a sort of a modification of the graph, and so on. So these are the steady state solutions.
Yeah, it's really impressive. So more question?
Yes, if I may, actually. Hello.
Hello.
Hi.
Yeah, hi. So I was wondering about, because you mentioned something about, no, one of your references referred to condition numbers. So I was wondering, how is the condition number of the iterates you get in your numerical solution strategy?
Yes. So let me go back to this third reference. So here in this third reference, we were looking precisely at the question of preconditioning of these problems, because the linear solvers really grind to the halt with some of these when R is close to 1. So when you're sort of close to Bingham, linear so iterative solvers are very slow. So if you look at the details of this paper, is that Gabriel?
Yeah, it's me actually. Yes.
Hi, Gabriel.
Yeah, hi.
I don't see
Hello.
a picture. I'm just guessing from your voice that it is you. So yeah. So if you look at the details in this third paper, we were looking at preconditioning. So what was done in the third paper is we used this diff-diff stabilization, like in Navier-Stokes. Then we were constructing preconditioners.
Okay. Okay, so yeah, I'll look at it. Thanks.
Thanks. Frederick, you are muted, I think.
I know that with Zoom, it's quite difficult to have some questions. So I think I know this talk is very interesting, and I want to do some example.
Thank you very much.
I don't succeed, but it is in my
to-do list.
To-do list, yes.
So what? So if I confess, so what is on the remaining slides is what is on my to-do list, and what is on my to-do list are non-monotone relationships.
Yeah.
So there are some numerical experiments, but this is sort of work in progress. So it's not really part of the talk. I'm very happy to talk about this at some other time, but so those are even more horrible problems, and there are physical situations when these non-monotone constitutive relations are important.
But the measure issue, if you are non-monotone,
exactly,
you have non-uniqueness of the solution in your law.
Exactly. You hit it right on the head. So what we can prove in that case is convergence to some kind of Young measure solution. And so, okay, so since you asked me, there is a theorem that you have convergence to a Young measure solution, and we have done numerical. So there's a non-monotone stress-strain relation, and what we see are oscillations in the shear stress, and these are precisely the kinds of oscillations that are reported in the physics literature in the stress, and we see these oscillations. So these red bits are oscillations in the stress in this non-monotone relation. But anyway, so there are lots of open problems to look at.
Yeah, that's really impressive.
Thank you very much.
So no other questions. So I think
there are questions. There are questions.
Oui, mais moi.
Yves is asking question. Look at the participant list. Yves Capdebosque is asking a question.
Okay, Yves, speak, but you are mute.
Okay.
Voilà. Hello, Andre.
Oh, Yves, hello.
I have a question about the beginning. Why do R graphs need to be R and R prime? When your R graph constitutive relationship, you put R on one and R prime on the other. Any reason?
So that goes. So let me go.
You put holder.
That's basically yes. It's basically Hölder. So just as in the case of Navier-Stokes, you end up with 2 and 2. So if you play this game with, for example, this power law fluid, you repeat this exercise with this power law fluid, what you end up is basically R and R prime. So it just comes out from the algebra. So you choose your model and you run through this exercise, checking this sort of maximum entropy production, and what comes out are precisely R and R prime. Or, I mean, you can generalize this. You can take a convex function and its convex conjugate.
Okay.
So it's somehow natural that these come out.
So Albert, you have the hand up.
Oh, no.
No, it's
Question.
just a mistake. So Vivette, no question? No, she disappeared.
If you want.
On audio, okay, there it is.
Oh, she's here, yes.
Yeah, I've been here all the time.
Oh, bonjour.
Excellent talk, very, very.
Thank you very much, Vivette. Thank you.
Very good. I enjoyed every minute of it.
Thank you very much indeed. You're very kind.
So no, I have no question for the moment, but I shall have a lot of questions afterward.
Okay, thank you. Thank you very much indeed, Vivette.
Okay, so for me, it's to continue the free frame days with the tutorial. So I will shut this Zoom and I reconnect the Zoom in 2 minutes to starting the tutorial things.
Thank you very much.
Okay,
indeed.
so thank you, Andre, for this excellent talk.
Thank you very much indeed.
And,
lovely to see you all. Lovely to see you.
Yeah, and I put your slide in the FreeFrame website. Of course, I think Francois do the same for the
yes,
seminar,
I think he did.
website.
Yes, Francois sent me an email to say that he did.
Already done.
Okay,
Thank you.
Thank you, Andre, for the talk. Very good.
thank you.
Bye, bye, Bernard. Bye.
Bonjour, bonjour Donatella.
Ah oui, bonjour, Donatella.
I know a lot of people.
Bye, everybody. Bye.
Okay.
Bye. Ah, bonjour Franco. So if you want to speak, but please do the micro. If you want to speak.
Se vuoi parlare devi...
No,
justement pour dire salut, au revoir, ça m'a fait plaisir de vous voir. Merci, Endre. Thank you, Endre, for your talk.
Thank you very much indeed.
Ciao, Endre.
Both of you, my God. Thank you very much indeed.
Bye-bye. Bye.
Bye. Okay, so I do that's of course nobody have the micro open, so you are nothing. And see you next time in next place.
Maybe in Paris.
Maybe in Paris or in Oxford.
Yeah, so
yeah, but remember that after the end of this year, it will be difficult to go in UK.
Don't tell me, I'll start to cry.
Yeah. Maybe.
See you.
Okay.
Bye.
Bye.
Bye.